Right, and the last presentation, finally, I'm glad to see that for this week. So it's the orthogonal diagonalization. So what's the problem? The problem is straightforward. So we have got a mapping phi from V to V. So an automorphism. V will be either real or complex with scalar products, so either unitary or Euclidean. And the question is whether there is an orthonormal basis in which A, the matrix, would be diagonal. And of course, if it's diagonal, then there is exactly the eigenvalues completed by zeros. And that's a question, under which conditions we can find an orthonormal basis. Orthonormal basis, that's crucial in orthonormal basis. That's the crucial thing to ask. And in the real case, it's quite straightforward and simple, right? Because the diagonal matrices, so if A equals D, so that's the case K equals R. So if the scalars are reals, then diagonal means self-adjoint. Self-adjoint. Wow. So it's the answer, right? So if in one orthonormal basis the matrix should be diagonal, then it means the mapping has to be a self-adjoint. And then vice versa, if it's self-adjoint, we saw already then that there is a basis which is orthonormal, in which it enjoys diagonal matrix, with the diagonal element being the eigenvalues, and all the eigenvalues are automatically real for self-adjoint ones. So that means that the diagonalizable ones are those which in any orthonormal basis happen to be symmetric. If the scalars are C, it's much more interesting. Because then the D equal always the real part of D plus the imaginary part, I times imaginary part of D. And so you will have a diagonal matrix with the splitting of the eigenvalues into the algebraic form. And of course, having such a matrix, the things commute, right? So if you multiply diagonal matrix with itself, so it's just the multiples of the eigenvalues there. And therefore, we see that the splitting of phi into, say, psi plus I eta, which we derived in the previous presentation, where psi and eta are Hermitian symmetric. So this is the decomposition as a sum of the Hermitian and anti-Hermitian part. And of course, if it allows the diagonal matrix in some orthonormal base, then of course the psi and eta must correspond to the real part of D and the imaginary part of D. And they have to commute, because we just know they commute in one of the bases, and therefore they commute as mappings. And this happens to be the complete answer. So if you look, so we just think already, or it intuitively seems to be obvious that that must be the clue. And so we look at what does it mean that these guys commute. And actually these guys commute if and only if the adjoint to phi commutes with phi. And this is computed very easily. It's just here, right? So you can compute easily what the phi is psi plus I eta, phi star is psi minus I eta. So the star really acts as a conjugation of the space of matrices. So maybe I should make this more explicit. So you can imagine you can imagine right, so you can imagine phi, again the same error, you can imagine phi star is simply the psi plus I eta, and the whole thing is star, and if you compute what it is, you get exactly, you can exactly get exactly this, psi minus I eta, right? Because psi is self-adjoint and eta is self-adjoint, and I will get just bar. So that's very straightforward. And then you see automatically that if you request that phi commutes with phi star, then the left hand side must be 0. That's the same thing, and this must correspond to having psi and eta commuting, right? So that's very straightforward. So in this sense, you can see the space of the complex automorphisms as a complex vector space, and each of them decompose into the real part and imaginary part exactly as the real numbers. The only difference is that whereas the complex numbers are commutative, the matrices are not. And if the real part and imaginary part commute, then it's the same thing as having the property that phi commutes with its adjoint. And here we have got the complete theorem, and it says that all the conditions, all 4 conditions in the list are equivalent. And the first one is the definition that there exists an orthonormal base for which phi will be diagonal. Of course, then it's diagonal in each in the corresponding, say, orthogonal base, because if you don't normalize the basis element, then it will result in some constant in the expression of the matrix, so it will be again diagonal. This is equivalent to see that the mapping phi commutes with its adjoint, and that's called phi being normal. So the normal mappings are those which commute with their adjoints. This is the same as the real and imaginary part to commute. And the final property is perhaps the most striking one, because it says that the sum of the squares of norms of all the elements in the matrix, so this is n square summand, or m is the dimension, is the same as the sum of the squares of the absolute values of the eigenvalues. And this is clear if we know that A is diagonalizable, then of course we can write it in the diagonal form in one of the orthonormal bases, and then there are just zeros except on the diagonal. On the diagonal there are the lambdas, so we get just the right hand side automatically, right? But what's not clear is that it's always all equals this. So one of the clues why it should be is to notice that actually if you make A times A star, so this is by definition always positive definite Hermitian symmetric. Positive definite means that all the eigenvalues will be positive. Well, semi-positive, right? So it might be 0. So if A is not of full rank, then there might be some zeros, but it's non-negative, right? So all the eigenvalues are non-negative reals here, and the eigenvalues of this matrix are exactly and the sum of the eigenvalues of this matrix is actually equal to the left hand side, but one has to think a little bit about. So it's clear that the left hand side is also invariant of the choice of the basis, because it's actually the sum of eigenvalues of this matrix. But on the other hand, what one can show is that for each mapping phi, we can always find some orthonormal base in which the matrix will be upper triangular. And here there will be 0. It's called a Schur's orthogonal upper triangulation result. So there will be something, and we shall come to this very claim. There will be the eigenvalues here, and we shall come to this claim later in some other discussions. It's not that difficult to understand. And then of course you see immediately that if you know that for each linear mapping you can find an orthonormal basis where the shape of the matrix will be this one, then of course you come already close to this, and this is the way how it's proved, right? So I will not go into further details, but this is a quite stunning characterization which works in general. But the most important one to remember perhaps is that once you look at our linear mappings from the point of view that each linear automorphism decomposes automatically in its real and imaginary parts, then we can find some orthonormal basis where the mapping will have diagonal matrix if and only if these two components, the real and imaginary one, commute. And this corresponds also to the fact which you can intuitively imagine, and it's not difficult to prove, and that is that two different linear mappings share their eigenvector spaces if and only if they are commute. So we simply want to get you know that for both of psi and eta they are self-adjoint, and therefore there is a orthonormal basis where the matrix will be diagonal, and those two orthogonal bases are possibly the same, so the eigenspaces will coincide if and only if psi and eta commute. So that's the message. So thanks, that's it for this week.